Welcome to Engineering Mechanics, Chapter 2, Statics of a Particle. Today we're going to introduce the concepts of forces and vectors. We're going to discuss vector math. We're going to discuss vector components. To do that, we're going to talk about the law of sine and the law of cosine, and we're going to talk about vector decomposition. We're going to introduce the concept of equilibrium and free body diagrams. The free body diagrams are a huge part of this class and will be extremely important throughout the semester. And after we do all that, we're going to expand the discussion into the third dimension. So we're going to look at the following things. We're going to look at the effect of replacing multiple forces on a particle with a single resultant force. We're going to look at the relations between forces acting on a particle that is in a state of equilibrium. And we're going to use these concepts on anything where the size and the shape of the body is insignificant relative to what we're looking at. Again, this is one of those assumptions that you might assume, you might think is too constraining, too limiting. But in reality, this is a useful thing. Consider a rocket. A rocket obviously is not a small object, right? And so when you think of the size of the rocket relative to what we're looking at, well, what if you're doing the guidance system? You're trying to dock a rocket with the space station. Well, relative to the Earth, relative to space, the rocket is a very small. The size and the shape of the rocket is extremely small and insignificant relative to the Earth and to space. And so that's an example where we can use these concepts to do work, to do very real work. Okay, so first let's talk about forces. What is a force? Well, a force is defined by the following. It's defined by its point of application, which ironically we're not going to talk about here in Chapter 2, but we will consider it in future chapters. And it's defined by its magnitude, and lastly by its direction. And direction kind of has two components to it. It has a line of action and it has a sense. Consider a vertical force. Okay, the line of action is vertical, it's up, down, right? But the sense is whether it's up or whether it's down. A vertical force could be up or it could be down, you don't know. The sense gives you the direction of it. Okay, combining forces. So experimental evidence has shown us that two forces can be replaced by a single resultant force using parallelograms. Okay, so what does this mean? Well, you come here. You have this force P and this force Q. You'll notice that it's a force in a direction and a force in a different direction, different force in a different direction. Well, if you draw a parallelogram with these two things, notice is parallel to Q and this is parallel to P, then you put the resultant force here, this R. This particle can be feeling, you can say it's feeling these two forces, or you could say it feels this one single force. And as far as the particle is concerned, it knows no better for it. It's the same effect on the particle. Now, these things, using the parallelogram laws, it follows the law of linear algebra, not scalar algebra. So 2 plus 2 doesn't always equal 4. What do I mean by that? Well, if you have, say, 2 pounds pushing up and 2 pounds pushing to the right, you don't have a total of 4 pounds pushing on this object, but you follow the linear algebra laws to find the magnitude that would be pushing it up and to the right. Okay, and for this class, and I think in general, vectors are going to be indicated in bold. So you'll have in print, it'll be capital, a bold P, or in writing with the arrow on the top of it, P with the arrow across the top again. Anywhere in text, you'll find it like this, but we'll do it like this when we're doing it by hand. Okay, an extremely important video.
Flight 209er, you are cleared for takeoff.
Roger. Huh?
LA departure frequency 123.9er.
Roger. Huh? Request vector. Over. What?
Flight 209er, clear for vector 324.
We have clearance, Clarence. Roger, Roger. What's our vector, Victor?
Howard radio clearance, over.
That's Clarence, over. Over.
Roger.
Huh?
Roger, over.
What? Huh?
Who?
What's your vector, Victor? Forces are vector quantities, so let's talk vectors. So first, let's talk some definitions. Okay, a vector, what is a vector? It is a parameter possessing magnitude and direction, which adds according to the parallelogram law. So some examples of vectors: displacements, velocities, accelerations, right? Magnitudes and directions. Versus a scalar parameter possesses magnitude but not direction. So examples of scalars are mass, volume, temperature, speed. Look at velocity, for example. The velocity tells you the direction and the magnitude, right? That's what a vector is. It's a magnitude and a direction. Well, the magnitude of the velocity vector is speed. So speed is the scalar, and the velocity has the additional information of the direction. Okay, a little more vector stuff. A vector can be classified in one of three ways. You have a fixed or a bound vector, and they have well-defined points of application, and you can't change those without affecting the analysis. Free vectors may be freely moved in space without changing their changing their effect on the analysis. And lastly, sliding vectors may be applied anywhere along their line of action without affecting the analysis. Okay, for two vectors to be equal, what does that mean? Well, it means they have the same magnitude and the same direction. Now, if a vector is the negative of another vector, it means it has the same magnitude and the opposite direction. Okay, let's talk a little bit of vector math, specifically addition. So vector addition follows a trapezoidal rule, which we just showed. Vector addition is commutative. So what does that mean? It means that the order doesn't matter. P plus Q or Q plus P, it's fine. Or P minus Q or P plus minus Q, it's all the same thing. It's vector addition is associative. So P plus Q plus S is, you can do it in different orders. You can add the P and the Q together and then add the S, or you can add the P to the sum of the other ones, so it doesn't matter. And it follows a polygon rule. Vectors add tip to tail, as many as you want. So say you have 27 vectors, right? So you can go from the tail to the tip, and then the next one starts at the tip with its tail and on to the tip and so on. And then when you're all done, you just start from the tail of the first one to the tip of the last one, and that's your new vector. That's a polygon rule. Okay, vector-ish multiplication. Okay, why do I throw in the ish? Well, because true vector multiplication is actually quite complicated, and we're not going to do it yet. But a vector can be multiplied by a scalar, and it is really simple. Okay, so let's look at the example P, the vector P. So P plus P is equal to 2P. Okay, I know that you don't think that that's anything special, but it actually is. What does that mean? It means that any scalar times a vector, it changes the magnitude by that scalar, and it keeps the direction. This is huge. This is going to be the basis for much of what we do in this class, that you can multiply any vector times a scalar, and you will maintain the direction of the vector, you'll just change its magnitude. Okay, resultant of multiple concurrent forces. Okay, for coplanar forces acting on a particle, remember coplanar, all forces can be replaced with a single resultant force with identical effect. Okay, so what is that saying? If you have 10 forces, you can replace, if there's 10 forces acting on this particle, you can replace those 10 forces with one special vector that has the exact same effect on that particle. This is the basis for moving forward, and makes our math much, much easier, and this is extremely important. So we can go from having many, many different forces, many different vectors, and we can replace them with a single force vector and have the same effect. Okay, so along those lines, often we want to rewrite a single force as multiple forces. It's called resolving into components. Okay, why in the world would we do that? We just talked about how we can take a bunch of forces and write them as a single force. Why would we want to go backwards? Well, say addition, subtraction, various other things. Sometimes you want to break things up into, say, the portion of the force that, consider a door. You're trying to open a door, so you're pushing on the door. Well, a portion of that force wants to open the door. Maybe a portion of that force wants to twist the door, which isn't going to happen. Or a portion of the force wants to, say, push the door into the wall, again, which isn't going to happen. And so you can break up the forces into the portions of it, the parts of it that you're concerned about. So really, there's unlimited ways to resolve these forces, but some of them make more sense than others. You know, obviously, considering, so chapter 8, we're going to talk about friction. We're going to talk about forces, you know, on a block, say on a sliding, on an incline. Well, maybe it would make sense to talk about, to break up the forces into the portion perpendicular to the incline and the portion parallel to the incline, right? There's all sorts of different ways to resolve the forces. You could do it all sorts of obnoxious ways, but it's really, some of them make a lot more sense than others. In order to do that, we're going to go back to a quick review of law of sines and law of cosines. So I'm hoping this is a review, not the first time you've seen this, and I'm not going to spend a lot of time on this, but Law of sines. What is the law of sines? Well, the law of sines says that the sine of the angle A over the magnitude of this of its opposite side is equal to the sine of this angle over the magnitude of this is equal to the sine of this angle over the magnitude of that. Or you can flip it all on its head and then this magnitude over the sine and so on. That's the law of sines. So when you know, say, a lot of times we'll know, say, this angle and maybe two distances. Well, you can figure out if you know this angle and this distance and this distance, you can then figure out what this angle is and so on. Okay, law of cosines. Law of cosines, hopefully this looks really similar. If you ignore this over, you have a squared equals b squared plus c squared. Nice Pythagorean theorem. Well, but the Pythagorean theorem is only good for a right triangle, right? It's only good for when the theta is equal to 90 degrees. Well, the law of cosines is how we deal with the theta not equal to 90 degrees. And so we have a squared is b squared plus c squared plus the portion of it that changes based on the angle being not 90 degrees. Again, law of sines and law of cosines, I'm going to rely on you either remembering it or going back and looking over this and spending a little bit of time on your own. I'm not going to spend a lot of time on it, but we will use it throughout, especially when we're doing these vector decompositions. Now, this last thing is a unit vector, and this is one where I'm not as sure it is something that you're familiar with, and so we're going to spend just a minute on it here. A unit vector, we're going to call it lambda, is a vector with a magnitude of 1 in a given direction. Okay, the whole reason a unit vector exists is to give you a direction. For those of you who took MATLAB or different classes around here, you'll notice there's two numbers that are kind of special, kind of convenient numbers to deal with. 0 is one of them. What's special about 0? Well, you can add anything to it, and you know what you're going to get. You know the answer that you're going to get. You're going to get whatever you added to it. Well, the other one is 1. So what's special about 1? You can multiply it by anything, and you're going to get that value that you multiplied it by. Well, so why does that matter with the unit vector? Again, remember, we just talked about this. We can multiply a scalar times a vector, and you'll change the magnitude of that vector, but you won't change the direction. Well, this unit vector lambda gives you the direction, and given that it has a magnitude of 1, it is defined as the vector that has a magnitude of 1 in a given direction. Given that, then you can go through and you can multiply it by some magnitude to change the magnitude, but you know the direction. So this is going to be a hugely important part of this class, is understanding these unit vectors, and we're going to use them over and over and over. Okay, let's look at some examples. Let's look at example 2.1 and 2.2 from the book.